Good day, ladies and gentlemen. My name is Precious Magodi, and today I am going to share with you a project that addresses one of the most critical challenges in higher education today. How do we make university admissions both fair and efficient? This research, conducted under the supervision of Professor Leung, tackles a problem that affects millions of students every year. Students who deserve opportunities but might be overlooked by traditional admission systems. Over the next few minutes, I'm going to take you on a journey from problem to solution, showing you how artificial intelligence, when designed thoughtfully, can actually increase fairness rather than reduce it. So let's start with the important question of why does this problem matter? Wow, imagine you're a brilliant student from a rural area in South Africa. You've worked incredibly hard to overcome significant obstacles and you are ready for university. But here's the problem: traditional admission systems are working against you. Right, these traditional admission systems face five critical challenges. First, equity gaps. Students from rural areas and low income backgrounds are systematically underrepresented, not because they lack the potential, but because traditional systems don't account for their their context. Secondly, processing inefficiencies. Universities have tens and thousands of applications. Manual reviews is just slow, expensive, and cannot scale up to those numbers. Then we've got poor resource allocation. And fourth, university seats go unfilled while qualified students are rejected. That's a lose lose situation if you look at it. Then, fifth, lack of transparency. Students are always left wondering, why was I rejected? What could I have done differently or better? Right? Now, here's the key driving insight for this project. What if we could use artificial intelligence not to replace human judgment but to enhance fairness? What if AI could actually help us see the potential in students that traditional systems usually miss? That's exactly what we set out to build. But obviously, before I show you our solution, it's important for us to understand what already exists out there and why do we need something different, right? Researchers have been working on AI for educational decision making for years. These are systems that predict student access, algorithms that automate application processing, and models that rank candidates. But here's what we found in our review: existing systems fall into a trap. They optimize for one thing, usually accuracy, but they ignore fairness. They predict well, but they perpetuate existing biasness. They are efficient, but they are not equitable. Some recent research has tried to address fairness, but it's typically added as an afterthought, a correction applied after the AI has made its decision. That's like trying to unbake a cake that turned out wrong. Well, our approach is fundamentally different. We don't add fairness as a patch, we bake it into the recipe from the get go. We don't use a single algorithm and hope it works. We use four different AI approaches and let them work their magic together. And most importantly, we don't just build a research prototype, we build a complete deployable system that universities could actually use tomorrow. So, let me introduce you to Admit AI. Admit AI is basically our answer to the challenges I've outlined. It's not just an algorithm, it's a complete ecosystem for university admissions. The system has three revolutionary components. First, the multi algorithm that is excellent. It features four specialized AI pipelines with each having unique strengths, working together like a team of expert advisors up there. Then we've got integration, not added at the top, but rather it's embedded into the very core of the algorithm, almost like it's embedded into their DNA. and it actively detects and mitigates biasness at every step of the process. Then we've got resource constraint optimization. Because universities don't have infinite space, our system balances academic merit, fairness, and practical capacity constraints. Now, let me take you inside the system and show you how each component works together to produce this amazing outcome. Right. So the components we start with data generation. This is where we get our data. So I'd rather say think of ADMIT.AI as a factory assembly line, but instead of making cars, we are making fair, accurate admission decisions. Let me walk you through the journey of a student's application through our system. So step one, they go through the data generation, which we will talk about and explain in detail. Then step two, their application goes through the brains of our system, which are the four parts, four algorithms, which we'll also break down in detail. Then they go through the fairness engine, and lastly, a simulation is run. Yes, the university can do sort of a futuristic projection of what the results would look like should they receive certain applications. Right. First of all, let's look a little bit deeper into the data generation. Well, one of the biggest challenges in building fair AI is getting good training data. You can't just make up numbers. You need realistic data that reflects the real world, right? So we started with census records, real demographic distributions from the statistics of South Africa, urban versus rural populations, income distributions, provincial representations, and so on. We then incorporated educational data, like the actual patterns in how South African students perform across different subjects, your mathematics, your physical sciences, your life sciences, your language. We later then studied the historical records. How have university admissions worked in the past? What are the patterns that exist? And we found those patterns. Right. Taking these three, we then fed them into our feature engineering, a system that identifies what actually matters for predicting student success, not just test scores, but context. A student who scores 75% in a well resourced urban school versus a student who scores 75 in a rural school with fewer resources, those two students tell very different stories about potential. The synthetic data generator then creates thousands of realistic application profiles, and our validation process ensures they reflect the reality of South Africa. This isn't just random data, it's carefully structured to mirror the real challenges South African citizens and South African universities face. Now, let's look at the heart of the system, the four AI algorithms. We start with our deep neural network, then we go to our hybrid gradient boosting, then we go to our SVR, and then we end off with our most creative ever, the neuroevolution. So, what I would like to say is that this is where ADMIT.AI gets really interesting, because instead of just putting all our eggs in one basket, we build four different parts. So basically, we've got four different baskets to put our eggs in, and with those they work together to produce the best. Why did we choose four? Because, well, different algorithms see different things. It's like getting four different doctors to examine a single patient. You get a more complete picture, and when they agree on a decision, you can be very much confident that the decision that they've taken is the right one. So let me show you how each algorithm works in detail, starting with the hybrid gradient boosting. Right, this is the architecture of the high gradient boosting. We start with input features where everything we know about the applicant, the grades, for their subject, their location, the distance from the university, their family income, and we feed that into as our input features. Then we do what we call a feature generation. We don't just use raw numbers, we create meaningful combinations and patterns. For example, academic achievement relative to school resources that are available for the student. Then comes the magic, gradient boosting trees. We build a series of weak learners, simple decision trees that focus on different aspects. So we've got a weak learner 1, weak learner 2, weak learner 3 that focus on different aspects. For example, weak learner 1 focuses on academic performances, 2 focuses on fairness, 3 focuses on contextual factors, understanding the full picture of the applicant when they are put together. But here's the key innovation. We don't just work with that, we have a fairness constraint built right in as the algorithm learns. It must also satisfy two requirements: demographic parity and equal opportunity. Right? We use a constraint solver to optimize for both accuracy and fairness simultaneously, not one or the other. Finally, all weak learners vote together in an ensemble voting, producing an admission probability plus explanations of which features mattered the most. The algorithm achieved a highest staggering value of 87.3 accuracy while maintaining fairness levels below 5% across demographic groups. I would say that's exceptional. Now let's look at our second algorithm, the Ensemble SVR. The Ensemble SVR, I'm going to fly through this. As we can see, that's our architecture right there. Um, Basically what it does is it takes in its features, which are almost the same as those of the previous one, but what's special about the SVR is it works with kernels that focus on different things. Like we can see, our RBF kernel focuses on academics, and then we've got one that focuses on demographic, and then we've got one that focuses on economic factors. Then we feed that into our fairness checks at the step, and then they all then vote and produce the output, which is an admission probability that represents the consensus of all three specialized models. Why does this work? Well, because different mathematical approaches can catch different patterns. What one model might miss, another one will catch. It's wisdom of a crowd, but for AI. Then our third algorithm is the deep neural network, the special one. If the previous algorithms are like careful methodological human reasoning, the neural network is like intuition, right? It sees patterns that are hard to put into words, things humans would never see. And that is because of its multiple hidden layers that have multiple neurons. As you can see, we've got three layers here with 120 neurons, and the other one is 64 neurons, with the other one sitting at 32 neurons. We again feed this into a fairness layer as we are going on, and then finally our output for this is an admission probability. Now for our most innovative algorithm, the neuroevolutionary approach. Well, this algorithm takes inspiration from nature itself. Just as species evolve to survive in their environments, our neuroevolution system evolves AI strategies to optimize for fairness and accuracy. We start with an initial population of 50 neurons, and then we feed those 50 into a fitness function which picks basically the top 30% as it goes to the selection process here. Then these top 30% are mixed together and they're evolved through mutation, and then again we select the best, then we specialize them, and then we generate a result. And our final result is a meta ensemble, basically a team of evolved AI specialists, each contributing their unique strengths. This approach finds solutions that human designers might never think of. Evolution is creative in ways we can't always predict. We can only dream of. Now that now I know you're probably thinking this all sounds impressive, but does it actually work? Well, let me show you a bit of the results. So the first results we see, what are you actually seeing here? This is our training phase, right? And it's the performance of our four algorithms. Let me break it down to you. If you look at our accuracy levels for the hybrid gradient boosting, I picked the lowest just to show you that at the worst it performs like this. Right, the hybrid boosting produced an accuracy of 62.3% at its lowest, and we've got our deep neural network at 50% with the SVR at 62.3 and our neuroevolution at 77.7. And but what I want you to take note of is, even though at their lowest accuracy where they are here and there making a few mistakes, we can see that the fairness level does not go below 75%. It is always above that, as we can see the lowest SRV being at 79.3%. We are just comparing the performance of the algorithms from the training data that we have. Looking at our results and comparing them to what already exists out there, we can see our system. The most important thing that I want you to see is our average processing time. Remember, we mentioned that manual systems take a very long time, right, to do all of this. As much as you can see, we have an average of 12 seconds that we need to run the system. Don't forget that we have done all of the things that all these other systems are doing. We are doing it all in one. For example, the NLP, it's just essay scoring and it does it in 8 seconds. But we take essay scoring, we take result scoring, we take all of those and we put them together and we make a finalized decision in 12 seconds. Can you imagine? That means processes that usually take 3 to 8 weeks, like we saw, will now take just maybe an hour at best, right? At most, I mean. Right, and also our system only needs 10% human oversight, right? Meaning the university can trust the system to bring them the best results possible without having to assist it, right? And we can see there the comparison with our neuroevolution performing at its best on test data, on actual simulations, right? Then we also have our fairness monitor. Looking at the fairness, it has a staggering of 83.6%, which is great. We can see the diversity index there at 97.8. We can see the overall equity at 83.6. We can also see the inclusion rate at 91.2%, and then the bias level at 16.4%. What's important here is we give the user an insight of the socio-economic balance. They need to watch out for this. Right, now I'm going to show you a live demo of how our system actually works. So this is going to be a short look into what you would do. So an administrator from the university will land on this page, and then they will log into the system, and then they will have a quick overview. What is the total applications that they have? What is the admission rate? What is the accuracy of all the algorithms combined, depending on the previous simulation that was ran? Right, I'm going to just show you a few things. Obviously they can set what algorithm they use as their default if they don't want to keep choosing and all of that. They also have some analytics here which shows them what has been happening in the last few 3 months, 30 days and all of that, with some data showing which courses are receiving the most students and all of that, right? Which algorithm has been performing best. They can see all of that under analytics. At data generation, they can quickly generate students the test data that they're going to use. We've already done this, so we are going to just skip it for now. Then they have a training center. We've already done the training center, and most importantly, on the training center, they can actually see a live log while the training is going on. Right, for the sake of time we are not going to show this. Then they can look at the fairness of the system, how fair, what they should watch out for, like they need to watch out for the social economic balance based on the last simulation that was run. They can also see a history of the applications that have been done and what decision the AIs have made. Right. Then what is important to them is them running a simulation. So they can press start here, which will start the simulation. So on start, they choose which algorithm they would like to work on. So I'm going to choose our best ever. They can also choose all of them, by the way, so maybe let me just choose all of them. Then also they can set how many students do they want to simulate with. For the sake of time, I'm just going to do a batch of 100. They can also set what is the admission capacity. I'm gonna leave it at 50, at 150. Unfortunately, this won't probably give us what we want to look for, but let's see what happens. Then, as you can see, these dots, these represent applicational students, and you can see how fast that went, right? What actually happened here is you started with blue, where the application was submitted, then it went to yellow, where the application was under review, then it went to purple, where AI where it was scored by the different algorithms that we might have chosen. Maybe it was a single algorithm, maybe it was two algorithms. Then they turned green to show that the students have been admitted. Don't be alarmed by why the dots are still moving. The most important thing is the color that they are carrying. If they are carrying a green color, they are saying, oh, all of the students that I have in the system have been admitted. If they were red, it would mean there were students that were rejected, right? um, yeah, and that's how our simulation works. We can reset, we can pause the simulation, reset the simulation, increase the speed of the simulation. Remember, our model might works with like 12 seconds to do all of these things, so meaning we can increase that and reduce that as time goes. And that's basically what the administrator needs to do. I just want you to have a look at this. You can see that the number has changed there, and the admission rate has also changed, as much as the accuracy there. It depends on what accuracy what happened on the last one, and then it averages it with all the other ones that would have happened. And right now we are sitting at 62.9, which we will increase in future. Right. um right, going back, what is next? So first of all, we want to optimize our AI models for better accuracy. Then we want to do a real world validation, where we validate this with real world data. Then if you have any questions, you can reach out to me or my supervisor, and we will provide. But before we end off, I just want to conclude by saying thank you very much for giving us time to listen. And also, we went out to achieve what we looked at achieving. We designed an multi pipeline, multi agent system that solves um, academic fairness, inclusion, and also maintaining efficiency. Thank you.